What's our big picture? So remember we said calculus is about one of two things. You know how much of something you have, and you want to know how fast it's changing. And then you know how fast something's changing, and you want to know how much of it you have. So what is our endeavor right now? Number one or number two? So do we know how much we have? We want to know how fast it's changing? Or do we know how fast it's changing? We want to know how much we have. A or B? B. Okay, that's our endeavor. We're starting with a rate function. We're starting with a rate function. Here's that falling ball example again. Okay, here's the falling ball example again. And we start with a rate function. Then what we do is, because it's a changing rate, how can we need constant rates in order to compute bits of accumulation like you did in your quiz. With a constant rate of change, you can calculate a corresponding bit of accumulation. So we take our rate function and we make a pretend rate function out of constant rates, trying to match the original rate function. Okay, and we call that step x. Here's a way of writing step x where we do it one constant rate at a time. So for every constant rate, we have to write that out explicitly. Okay? And then last time in class, we defined step as one rule, and we're going to review that again today, okay? So rather than have to write out 0 and write out each individual rate separately, we want to write step x in one formula. And we've done that, and we'll review it. So hopefully many of you are thinking what that is. You know what that is already, okay? Because we have done that. Okay, so that's our approximating or pretend rate function from which we build the accumulation function, right? So we know how fast it's changing, and we want to know how much of it we have. So is this accumulation function based on this step function, is it approximate or exact? Is it approximate or exact? It's approximate because it's based on an approximate rate function, right? Since we have constant rates, result in linear pieces of the accumulation function. Okay? So we start with exact rate. We build an approximate rate based on constant rates, from which we get an approximate accumulation function, which is piecewise linear. It's pieces of lines. Pieces of lines. Okay? So the next thing we want to do is, rather than have a separate formula for every line, a separate formula for every segment, we want to write this in one formula. So we want to write something like this h of x formula. We want to do that instead of breaking it up by interval. We want to write that in one formula. That's by the end of today. That's what we hope to accomplish. Okay? And then from there, we'll have our approximate accumulation function, and then we'll want to get the exact accumulation function that matches our exact rate function that we started with. Okay, so that's the process. Exact rate of change, the pink graph, to approximate rate of change, which is the blue step function, to approximate accumulation, which is the red piecewise linear graph, and then the last step would be to get exact accumulation, the exact accumulation function. Okay, which means for any value of x, that function will tell us what the total accumulated amount is at that value of x. Okay, so let's review this thing. Let's review step. Okay, so I think a good way to help us review this is to review these three functions. Exactly what are these three functions? So I want you to take a couple minutes. Oh, you can't see it. I'll sketch on the rate function because you can barely see it. But take a few minutes. To understand a function, first and foremost, means understanding exactly what its input is and what its output is. So what does each thing do? What does left do? What does it take and what does it give? What does R do? What does it take and what does it give? And what is step? What does it take and what does it give? So super important that you understand these functions in terms of what are their function, what's their input, and what's their output. Okay? Go. Okay, what is the input into left? What's the input into left? What quantity is the input into left? There's some people saying x, right? Any x value. And so we think of that at the current x. So this blue x that's increasing, we think of any x value swept along there would be an input into left, okay? And what's the output of left? Is it a rate of change? Is it y? So this is what's confusing about this. You're used to outputs of functions being a y coordinate. That's not what left is. What's the output of left? It's another x coordinate, right? It's the x value at the left end of the current interval. What I'm showing there with a hand as x sub L. What? Yes, left of x is the output, which is the function way of saying x sub L. All right, what about R? What's the input into R? It's also x, right? So any x value. Okay, what's the output of R? Okay, what rate of change is it? Is it a constant rate of change? Exact or approximate? R. R is the exact rate function. It's the actual rate of change at x. R is the curve, right? It's the curve. It's the rate of change function we started with. Okay? What's the input into step? Okay? Again, any x value. Any x value can go into step. And what's its output? Is it another x value or is it a rate of change? Okay, approximate or exact? This one is, so the step function is the one that's being drawn out here in this animation, right? These gray steps. That's the step function. It's the pretend rate of change function. Step is the pretend rate of change function. Okay, so let's just practice here. So if I make the x equal to 1 here. So if x equals 1, I want you to tell me what the output of left of x is, the output of r. So if you can do an exact, if you can express it exactly, express it exactly. If you need to approximate, do an approximation. But what would left of 1 be? What would r of 1 be? And what would step of 1 be? Go. What's left of 1? What's r of 1? What's step of 1?
So that would be yeah, and then the step thing would be for R. Rate is happening. Oh, yeah.
Okay, what's left of 1? Left of 1 is what? What would you say left of 1 is? Okay, that's only because you can read it. But if you couldn't read that, what would you say? What's left of 1? A. These are x values. A, B, C, D, E, F. Those are x values, okay? What is r of 1? What's r of 1? What about 0.1? Is that what r of 1 is? No. What is r of 1? It's like 0.2. You should be thinking it's 0.2. It's the actual rate at 1. Where do we get that from? The curve, the y-axis. The actual rate at 1 is the y value of this point. The actual rate of change at 1 is the y value of this point on the r curve. So about 0.2. What about step of 1? So that's about 0.1. Okay, how could we express that exactly? So it's about 0.1. How do we express that 0.1 exactly? R of A. Do you see that? It's R of A. Questions on this first example of at x equals 1? Left of 1 would be the x value at the left side. It'd be A. So that this left function is different. You're used to a y value being the output. The output of left is another x value. The x value at the left side of the current interval. So in this case, that's A. All right. The actual rate at this x equals 1 is the y-coordinate of the point on the curve. That's around 0.2. And then step of 1 would be the rate, the real rate over here at the left side of the interval, R of A. Questions on that? All right, another example. Let's do x equals 3. Go, x equals 3. Okay, left of 3. Left of 3.
D.
You said D. Is it D? Yes. R of 3. All right, now I can give you a little help here.
That would be about 0.75.
Yep. About 0.75. It's the y-coordinate of the point on the R curve, right? It's the y-coordinate gives that actual rate at 3. So it's about what's that, 0.75?
Yeah.
All right, what about step of 3? About what? About 62? Yeah, about 0.62. How can we represent it exactly?
R of D.
It's the rate at the left, at D, R of D. How'd you do? Did you get them all right?
Yep.
Okay, so we really need to understand each of these functions individually. Okay, to make so now we see that these are acting together. So this point right here has coordinates 3, step of 3, right? That's our approximate or pretend rate of change when x equals 3. Okay?
So it's not an actual value, it's just the pretend rate at
Well, it's the actual value of step.
a step. Okay, yes.
It's the actual output value of step. But step is pretending to be R. It's pretending to be R. Okay. So, but what did we say step of 3 was? R of D, right? But wait, but look what I just did. I just made all those x values disappear, so I can't use D anymore. I need something else. How can we express D? How can I express? So everyone should know this. So if the D's gone now, we don't know what value where it's pointing is. We don't know its value. We need to express D somehow. How do you express D? How can I express D? What do you think? Yep. What do you think? So D is the same as left of 3. So if I didn't put any values there, you can't write D anymore. So our D is left of 3.
Nice.
So that's why. So in the end, step of 3, right? Step of 3 equals what? R of left of 3. You take 3 and you find the left side of that interval to get that x value, and then you plug that x value into R, and that gives us, so we take 3, we plug it into left, it gives us that x value. We plug it into R, it gives us that rate, which we're going to use as the y-coordinate for our rate at 3. So that's why step of 3 is equal to R of left of 3. This is how we can write now this step function. Instead of writing out a separate value for every constant rate and doing a big piecewise function, we can write it now in one line. Step x is, so for any x value, How do you get the approximate rate at that x value? First you take the x and you do what? Do left x. And then what do you do with that? You take that x value, right? The output of left x is another x value. We take that x value and we input it into R. And that gives us the approximate rate at our x value, right? So the approximate rate, the actual rate at the left side, that's what this is the approximate rate at our value of x, right there. So that's writing step x in one formula. So what made that possible? This kind of complex formula for left x. The fact that as x moves through the intervals, left x stays constant through the whole interval, and then you move into the next interval, and left x changes, right, to the left side of the new interval. So that left x function makes this writing the step x function in one line possible. The hard work we did to develop left x makes step x easy. You just take that left x value, plug it into the rate, and it gives us the approximate rate of change at the current x. Okay, so does this help? Does this help clear things up? Any questions? Anybody have a question?
When we use this,
What's that?
I'm just trying to figure out when to apply this now. Like, I'm not. It's a bad question. You know what?
So we're on this journey of we know how fast something is changing, and we want to know how much of it we have. And in order to do, given a rate of change function, which realistically is a changing rate, we need constant rates to get bits of accumulation. And so so we're writing this function of these constant rates in one formula. So now the next thing is, now we're going to take this constant rate function and make an approximate accumulation function in one formula, rather than all those lines pieced together.
That actually is a question.
Okay, so let's do that. But before we do that, more review. Okay, so I've got some review questions for you here. So this graph below concerns the value of y of some quantity with respect to another quantity whose value is x. Okay, the blue graph is r, the pink graph is step. In your homework, you looked at a variation on left called mid of x, right? The mid function. That takes the actual rate at the middle of each interval and makes that the constant rate for the whole interval. Okay, so that's what you're looking at here. Let's see. So you're going to take some time to work through these. Are, again, review questions, okay? We want to make sure we really are solid in what we've done so far before we go on to this next hard part of writing the accumulation function in one formula. All right, so let's go back to first three. Let's do the first three. Go. All right, where's Caitlin Ross? Oh, it's a question? So what are the specifics about the step graph? Like there's lots of different variables related to a step graph in terms of let's just answer it. I think it'll help. Question over here.
So, is this the x value in the step? Is that mid of x, or is it like less than x?
Okay, so how? All right, we'll get to that in number 2. So let's just talk through these. Where's Caitlin Ross? Where's Caitlin? All right, how about number 1, Caitlin? What kind of function is the curve, the blue curve? Okay, so something, she says R is a rate of change graph. So the input is? It could be time. Often it's time, or it could, like if in the tax function, it could be taxable income. Right, so the input is our x or independent quantity, and then the important thing is what kind of value is the output of the blue curve? Rate of change, right? So the y coordinates on this graph are rate of change, a relative size of a change in y to a change in x. So this 0.5 right here would mean the change in y is half as much as the change in x, rate of change. Okay, what kind of function is a step graph? What's the input and output of that? Different or the same, input and output? Okay, the input, same or different? Same. Output? Well, you could argue it both ways, right? So what about the units on the output? Same or different? Same. It's trying to be, the step function is trying to be like the R function. It's trying to mimic it. It's trying to replicate it. So it has the exact same output units. The difference is that the curve is an exact rate function, and the step function is, since it's only trying to mimic it, it doesn't do it exactly, so it's approximate. Okay? But in terms of the units, what the kind of thing they're outputting, they're exactly the same. They're both outputting a rate of change with the exact same units. Miles per hour, or degrees per minute, or tax due per dollar. Okay, and why do we create it? Why do we create the step function? We've said it many times. If we've got the exact rate function, what are we doing making this other rate function that's not as good? It's approximate. Why?
Because it's not constant, so we want to find KS being constant.
We need constant rates to actually be able to make some progress towards accumulation, right? We need constant rates to actually be able to get changes in accumulation to build an accumulation function. As long as that rate is changing, we're kind of stuck. Okay? All right, what are the specific characteristics of this particular step graph? So is it a left graph? No, what is it? It's mid. Meaning, instead of taking, so I should say, it's not mid, it's based on mid, right? It's based on mid. Not based on left, right? So now, to get the constant rate, we don't look at the x value at the left side of the interval, we're looking at the x value at the midpoint of the interval, taking that actual rate and making it the constant rate for the whole interval. What's another characteristic of this particular step graph? Delta x is 0.3. Anything else we can say?
A is 0.
A is 0. Good. So we're starting accumulating at 0. We're using intervals of 0.3. And we're getting those constant rates by looking at the actual rate at the mid of the interval, not the left side. Okay, more questions? Yeah.
So how would you want us to, how would you step that? So would you put in like an X value?
No, it's just talking about any x value in that interval.
Oh, okay.
It's talking about any x value in that interval. So like it's giving examples here in part B. 0.66, 0.87, any x value in that interval.
Yeah, so
I think that's the start of step.
step of X. Okay, left.
So you say A of 5 to 3.6 would be the value for that. So you would give the exact rate. Oh, wait. A value between the first step. So rate is
Okay, where's Stephanie went? Where's Stephanie? How'd you do on, go to part B. How could we rewrite exactly what, say, step of 0.87 is? Did you get that? She wants R of 0.75. What do you think? Is it right? She wants R of 0.75. Is it right? Yeah, the midpoint of this interval is the x value 0.75. We're going to take the rate there. And that will be the rate everywhere in the step function for that interval. So all of these y values of this step are the actual rate at 0.75 at the mid. Nice. So what does this have to do with this expression here? So what interval are we in from 0.6 to 0.9? 1, 2, we're in the third interval. So what does that value have to do with this expression? Which k?
Third.
That's this right here. That R of 0.75 is the constant rate we're going to use, the third one for the third interval. Does it make sense? See this? Okay, cool. So how can I write step X in one formula? How can I write step X in one formula? R of mid of X. Who got that before I started writing it?
What is our
X is any value, right? Because we said we were in the third interval between 0.6 and 0.9. And so the constant rate in that interval is based on the actual rate at the midpoint of that interval instead of the left side. So before we were doing like R of 0.6. But now we're looking at the mid, so it's the actual rate at the middle of the interval. And 0.75 is halfway between 0.6 and 0.9. 0.75 is that halfway point between 0.6 and 0.9. Okay, so step X now is R of mid of X. R of mid of X. Okay, let's keep going. So now we're looking at this big expression here, and now we're going to start relating. We're relating all this stuff about rate of change in the graph to this long expression. Okay, so go. So start with number 6. Not going to make it. No, that's exactly halfway between 0.6 and 0.9. It's the mid of this interval.
So you couldn't figure it out by using like the mid equation with its like left of x plus half of these.
Yeah, if you do left of x plus delta x over 2, that's a mid x formula. You put in x and you get the mid value of x.
How does the sum show
Yeah.
Okay. Oh, I see.
Okay, so is it okay if I keep you like 5 minutes over today? Yes. You say yes. Yes, teacher. Okay. Just want to give you fair warning. Don't pack up at 10:15 because we want to get to the big conclusion here. I'll move as efficiently as I can, but I don't want to lose you. Also, okay, I don't want to lose you. All right. So each of these, you should have said that each of these is a bit of accumulation. Each one of these k delta x's is an amount of accumulation taken from that respective interval. So you got, how do things accumulate? Bit by bit by bit by bit. And we add up the bits, right? We add up the bits to get the total accumulation. So each one of these terms is the accumulation from that interval. And then the whole sum then is the total accumulation from the first 10 intervals. Good? Are we good there? Okay. So what part of the sum shows the accumulation starting at x equals 0 up to 1.2? What part of the sum shows the accumulation starting at 0 up to 1.2? This right here? Does that show what that is? That the answer to 7? No, all of these together, right? The answer to 7 would be the sum of the first 4 intervals. Is that right? First 4? 1, 2, 3, 4. The sum of those first 4 terms would be the total accumulation up to 1.2. All right, what about the accumulation up to 2.2?
The first 8.
The first,
The sum of the first 8.
sum of the first 8 intervals. Well, that would be from 0 to 2.4. So something's different here. Something's different about this question. What's different about this question? We're going to add up the first 7 intervals. Is that going to give us what we want? No. Then there's a partial interval, like you did in the fireworks problem, right? That last one was you took part of the interval up to 2.8 seconds. So it's going to be, we're going to have, let's do summation notation. So say j equals, we're going to do 1 to 7 of kj delta x plus, we'll just say accumulation from part of the eighth interval. Doesn't make sense. So we can use that summation notation to get the first 7 intervals because they're all the same. K delta x, K delta x, K delta x. But then that last piece is different. It's a shorter interval. It's shorter than delta x, shorter than 0.3. So we've got to calculate that kind of separately. Does this make sense? So this is actually going to be the form of our one line. This is going to be like the general structure of our one line accumulation function. We're going to sum up all the whole intervals and then add whatever partial interval we have, wherever x, to whatever the current value of x is. So this is the general structure of our one formula accumulation function. Yeah?
How can we use the k value as a constant, the same thing as different k values?
That's where the j comes in, right? K of j. So j is going to cycle from 1 to 7, and each time we'll have k1, k2, k3, k4. So that's the beauty of this summation notation.
Thanks.
We can show different k's. Other questions before we go on? Okay, here we go. Okay. All right, now I'm going to switch to left, where we're more comfortable. So switching back to the left sides. All right, so a of x is going to be our accumulation function. It's the accumulation of the quantities starting from a up to the current value of x. So represent a of 1.2. We said it's the sum of the first 4. But what specifically are the rates? We need to get those rates as a function of they're going to be r values. So we're going to find out exactly what those rates are. So what's the first rate? R of what? 0, right? If we're using left now. Now we switch to left. So that first rate will be r of 0. What will be the next rate? R of 0.3, which is really the starting value 0 plus going over one interval, right? 0.3. What is the next x value that will give us this third rate? 0.6, right? Which is, we start at 0 and add 2 times 0.3. Does it make sense? And then, for the fourth rate, we'll start at 0 and we'll go how many 0.3s? 3 over, right? Which will be 9.9. I'm just picking off. What am I doing? We're just taking the left x value for each of these rates, but I'm creating it as an expression starting from 0. So the first one's 0. The second one's going to be 0 plus 1.3. And the next one is going to be 0 plus 2.3s. And then 0 plus 3.3s to get to, so we know this is, this is 0.3. This is 0.6. Should feel very comfortable, just like left, right? Just like the left function. It's the left x value at each interval. So K1, K2, K3, and K4. Are we good? So now we want to generalize that. Generalize that in terms of a and delta x. To write the exact same expression, but instead of using the particular values here, what would it be in terms of a and delta x? R of what? Remember, a is our starting value, delta x is the width of our interval. So R of what?
0 plus 1.
No, we're going to do everything in terms of a and delta x now. A. Okay? What's this one? A plus 1 delta x, right? What's this one? A plus 2 delta x. And then? Does it make sense? Following. Okay. So now I want to write this in summation notation. So so j counts the interval. This is the first interval. This is j equals 1. This is j equals 2. This is j equals 3. And this is j equals 4, right? J is the interval number. So I need a formula of a, j, and delta x that's going to give me the right x value for the jth interval. So in the first interval, how many delta x's do we add? 0. In the second interval, how many delta x's do we add? Listen, in the second interval, we add 1 delta x. To get in the third interval, we add 2 delta x's. Into the fourth interval, we add 3 delta x's. So how many delta x's do we add to get to the jth interval? Always 1 less. It's always going to be 1 less delta x to get to the left side of the jth interval. So we're going to start with a, and we're going to add j minus 1 delta x. The first interval, j equals 1, we add 0 delta x's. In the second interval, we add 1 delta x. In the third interval, we add 2. So in the jth interval, we're going to add 1 less than j, delta x's, to a to get that rate. Anybody have a question? Does it make sense? Okay, so the video is rolling. You're going to want to review this, okay? You're going to want to review this.
Last videos.
Okay, what about a of 2.2? What did we say? First 7 intervals will be just like what we did before, plus a little more, right? First 7 intervals plus a little more. The accumulation from part of that last interval. So the summation for the first 7 terms will be what we just found, right? If we have whole numbers of intervals, intervals, we're going to add 1 less delta x than the interval we're in to get to the left side of that interval. We just saw that worked out. Okay, plus a little more accumulation. Well, that's going to be K8 times 0.1 instead of 0.3. So we're coming to here at 2.2. So we've got this is K8 times that amount of the partial interval, that little width there, 0.1. So we can express that as, that's the K8, and we can express that little partial interval as 2.2 minus 2.1. Okay, well, what is K of 8? It's r of left of 2.2. And what's 2.1? Left of 2.2. Okay, so A is the starting value, X is the current X value, where we're accumulating to. Left X is the X value at the left end of the current interval. And so A of X is the sum of bits from full intervals plus a little bit more from a partial interval. So we saw how we figured out how to sum up bits from the full intervals. The question is, how many full intervals? How many full intervals? We've done this before. What's the key? How many full intervals? The floor function of x minus a over delta x. That's how many full intervals we have. And then we're going to have this little bit more, which will be r of left of x times that part x minus left of x. So there's our accumulation function in one formula. Yeah, we looked at this like a month ago, and it probably hurt your eyes, but now we understand every part of it. So You will be working over the weekend on homework to keep understanding this. Okay?